Hi all, thank you for coming to the internal cycle of seminars of the INEDEA. Well, today Rotman Criollo is going to present a little part of his work. He's a postdoc that is added to the Global Change department. Yeah. And well, thank you so much for collaborating in the seminars.
Thank you, Chica.
Go ahead with the talk. Thank you.
Okay, thank you for coming. Well, I will explain some briefly the work that I'm doing here. It's related with groundwater and geothermal systems, specifically in coastal aquifers that here in the island, most of all the aquifers are coastal aquifers. First of all, I want to explain very briefly what are the water cycle and how groundwater is included in it, because sometimes there is only some small lines in the bottom of the figure. Okay, but here the movement of I use this, right? This is groundwater. Okay, so water goes to the atmosphere, rains, it's precipitation, and the water bodies that we saw are lakes, rivers, and sometimes you can see some springs like seawater. Okay, but there is not common to see groundwater. So sometimes it's not well known what is going on in our feet, above our feet. So there are some pathways that allow to infiltrate this water from surface bodies, water bodies, sorry, and goes to the aquifer. So, but at the same time, this water goes with some chemical compounds, so pollutants for us. And there are some fertilizers, fertilizer emissions, waste, and there is widely installed in urban areas some drainage systems that allows to infiltrate urban water and at the same time reduce the runoff of rainfall events, mostly the extreme events. But at the same time, this water allowed infiltration of pollutants. Okay, other pathways of pollutants that arrive to the aquifer are leakages of sewage networks, but also for drinking water supply. Additionally, we extract this water to different purposes, for instance, for irrigation, or drinking water, or clean infrastructures, and so on. This extraction of water reduce the water levels and may produce some problems in the surface. Let's say some down of the land that may produce some cracks in some buildings and reduce the porosity of the porous media that reduce at the same time the groundwater flow. Other problem that has is the urban infrastructures like tunnels, that there is a barrier of the natural water flow that goes to the discharge areas. These discharge areas are water boundaries, water bodies like lakes or the sea or the ocean. The velocity of groundwater is very slow. Okay? We work with meters per day. So it's very slow. It depends on the geology, it's more quickly or less. For instance, here in Balearic Island, we have karst. There are caves, holes that is like it acts as a river, but it's not the common. In all the geological materials, we will find water. The problem is that the velocity that we can extract. Okay. If we extract this water, mostly close to the sea, we make the seawater goes to the inland and increase the seawater intrusion. The problem of this is that we put more salinity in the groundwater. So sometimes we call that this water is contaminated by saltwater. We cannot use directly for irrigation or drinking water or drinking this water. We have to do some treatments before to use. Additionally, now we are using the surface for extract energy, the geothermal energy. That we use the natural heat that the earth has to obtain electricity or use for conditioning some buildings. So I will focus in this anthropic uses for geothermal energy. That is a renewable energy because we use a natural temperature from the earth, and the more deeper that we go, the more temperature that we will have. Okay, so there are three main uses of geothermal systems. The first one is that you think about energy is electricity, but electricity is not the often use of geothermal energy. Okay, so we will have to do boreholes more than 2 kilometers to find temperatures higher than 150 degrees. Okay. The second type is to district heating, that we have enough temperature at different depths that share this energy with different buildings, with different uses. As there is a share of energy in a specific area, like let's say a neighborhood, a big industry area. But the most common nowadays is the geothermal head, that we drill 100 to 200 meters to find more or less as average 20 degrees. Of course, there are different places. There are the heterogeneity of geology makes that sometimes in this range of depths, we can find higher temperatures because of geothermal anomalies. Like in Llucmayor, we have a hole that it doesn't have the regular law of geothermal gradient. Okay, so how works the geothermal systems for extract electricity directly? So mainly we use binary cycle power plants. That is called because we use two fluids. It's not mixing these two fluids. This exchange energy in a heated exchange that we extract hot water from the underground and exchange only the energy in this compressor, is like this machine, and exchange this energy to stem the liquid and move a turbine and generate electricity. Okay, but to install this kind of geothermal systems is very it's not common, and you have to find volcanic areas or rift areas where you have increasing of temperatures that goes to the surface. Okay, because the less that you drill, the less that the budget will be lower. Okay. Additionally, the district heating and the heat pumps, we are talking about less than 500 meters, and there is a closed loop. We have some pipes distributed in different strategic designs to optimize this exchange. Okay, so we pass a fluid through these pipes, circulated liquid, and it depends if we want to cool or heat. We inject cold or hot water. Okay, so this liquid used to exchange like before with a heat exchanger to aconditionate our buildings. These buildings is not only houses, but I will explain later other purposes. Okay, so what happens in winter? We obtain in general, as summary, we use the seasonal temperature difference of the specific of the space, and then we use this temperature for heating or cooling. In winter, that is called the surface. We obtain this cold. We inject in these pipes, and then through these pipes, it's heating this liquid, and then we use this heating to condition the building. In summer, is the opposite scenario. We use the hot of the summer to cold this liquid and condition the building. Why is important is because, for instance, in European Union, it's more than 60% of energy that we waste for space heating and space cooling. Okay, we don't have to consider the water heating or cooking, or well, this is not the common use of geothermal systems, so we cannot see this 40%. Okay, but there is a lot of energy. So geothermal systems can be very useful to reduce the use of fossil fuels and increase the independence of external incomes of energy. For instance, in the island, that is very, very, very important. So the uses are very common for tourism, for conditioning different installations, agriculture for crop or for agriculture, and industry for different purposes, that industries that requires very constant temperatures. For instance, I'm talking about the shallow geothermal system that can be conditioned for heating or for cooling, okay? Not electricity in that case. Other purpose is very interesting for computational servers that you have to cool and stay with a constant temperature, okay? Or hospitals, for instance. This is the motivation of the Cool Coast project, that was to understand the effects of shallow geothermal system in coastal aquifers. Okay, but to achieve that, I made 4 scenarios of modeling geothermal installations. Okay, so the first one simulates constant cold requirements. That it means that inject cold. The second scenario, cold requirements that inject hot. Okay, it's the opposite, because when we want to cool the building, for instance, in summer, there is very warm the atmosphere. Okay, so we inject this warm in the subsurface, and the opposite for winter. Winter, the surface or building is cold. This cold injects in the surface and extracts heat. Okay, and the third and fourth scenario is a symmetric cycle of injection, cold and heat. Okay, the third starts with 8 and finish with 8, and the fourth starts with 28 and finish with 28. After 4 cycles of these injections, we stop the operation and see what is going on with the temperature of the groundwater. How is the recovery of the temperature, the initial temperature, what time it takes, what is the behavior of this, what is the shape of this recovery. Okay, so I use the free flow numerical model code to couple mass balance of flux, solid, and heat, and all are coupled with the difference of density and difference of temperature. Okay, this is the stem of the model. There is a 2D indeed. It's like a piece that we cut the aquifer until it arrives to the sea. Okay, there is the sea. This is the sea. More or less like this. This is the sea. In that place, in the left side of the model, I put a constant condition of hydraulic pressure, of freshwater pressure, that is changed because of the density of the seawater. Okay, because of the environment. Using the density, we can equal the pressure from the freshwater than the seawater. Okay, the seawater that goes from the inland to the sea, that is discharged in this direction, is a constant flux with a constant a constant concentration of 0, while in the sea side is a constant concentration of 1. Okay, all the model has the same temperature, is 18 degrees with these parameters that I don't explain now. Okay, this is the results. In that point of the model, that there is this point, we have the groundwater flow that goes in that direction, while the seawater goes in that direction. It goes to the inland because the pressure of water here and because of the difference of density. As you know, the more density is more its weight is more heavy and goes to the bottom of the aquifer, while the groundwater goes from the top. It's like it's a floating with the fresh water. Okay, then there is a mixing zone, of course. It depends on the hydraulic parameters, what is going on of the geology, that the shape of this seawater interface is different. Well, what happens when we inject only cold? That is the dashed line, the gray dashed line, is what is going on in that point, in the middle of the geothermal exchange, that there is a line. And in the orange line is the temperature that arrives here. Okay, so we see that we arrive to 12, more or less 12 degrees here constantly, while in the second scenario, that is only heat, 28 degrees constantly injecting, we arrive until more or less 25 degrees, constantly arriving to the seafloor for this big point. Okay. What happens here? That we saw that when we inject only cold, there is a delay to arrive to the initial condition that we passed more than 10 days, 10 years, sorry, and we don't arrive to the gray line. Okay, so it takes a long time. The same for only 28 degrees, but in that case, we are it's lower for the initial condition, and it takes more time to arrive to the initial condition. What happens when we we play with 8 degrees, 28 degrees? So what we see that we are injecting here, we are injecting hot 28 degrees, and then in the seafloor is arriving lower temperature. And the opposite, okay. So if we inject hot 8 degrees, there is arriving more temperature than the initial temperature, okay? So there is a delay more or less of 6 months to arrive the thermal plume from the point injection line to the seawater discharge. And then again, we can see here a little thermal hysteresis that delay to arrive to the initial condition. This is what it looks the temperatures in the profile. Along this profile, this is the piece of the model that I showed is that region. This orange line is the coastline that the seafloor, sorry, that, and the coastline that is in this line. So sorry that you can, I don't know if you can see here very well. And because of this flux of salt water, this salt water push the temperature to the inland, arriving to the toe of the seawater intrusion. Okay, what happened here? We are cooling this area, this seawater interface, reduce the density and viscosity. And what happens when we reduce the density and viscosity? It decreases the velocity. The seawater, the groundwater that is discharging here is have less velocity, more soft, not so much, okay? But at the same time, this water is more heavy and push this seawater interface to the sea. Okay. The opposite scenario is when we inject hot, that increase the density and viscosity and increase the velocity. It means that the groundwater flux is more faster to the seawater discharge. At the same time, is by effects of buoyancy, this seawater interface goes up. And at the same time, the toe of the seawater interface goes inland. So we are increasing the seawater interface. When we play with these 8 and 28 degrees, what happens was more or less the same. Well, the case of when we inject cold is pushing the seawater interface to the sea, and when we inject heat, it's a buoyancy effect that goes up. So it's like in that manner. We can see a video I can show, sorry, but it's like this. It's like a line of guitar, more or less. And it moves a little bit the toe. So this is the point of reference if we are increasing or reducing the seawater intrusion. But yeah, and that's it. And then other interesting thing is that when we are oscillating, that is the most common use of geothermal energy, because in winter we inject these cold water, cold temperatures in the ground and obtain cold. And at the opposite is the most common. We arrive in the seafloor after 6 months, more or less. It's arriving in winter 22.4 degrees in the seafloor, in the coastline, and in summer 30.6. The initial temperature of groundwater is 28. 20. Sorry, 20. 1.18. Okay, and yeah, that's all. It's as a conclusion, we can see that if we inject cold, we are pushing the seawater to the sea. And at the same time, it takes more time to recover the initial temperatures. And at the opposite, when we inject cold, we are allowing the movement because of the buoyancy of the seawater interface goes to the inland. Okay, and it takes less time, more or less, 100 days more or less. And I need to study more in these things because, of course, there is a theoretical example. The geology plays a very, very important role here, of course. Additionally, the shape of the coastline, what is going on with the hydraulic dynamics in groundwater. And of course, if we put more anthropic uses with extraction at the same time, with other geothermal systems playing at the same time, it is more complex and I need more time to study. But the more important thing is that geothermal systems, it should be to include in the coastal management plans, not only for this, because for groundwater also. I don't know if in the coastal management plans consider groundwater discharge, I don't know. But I think that is very relevant. Thank you for your attention and see you upstairs.
So I actually have a few questions. So I guess some of them I'll ask you. If you, I didn't understand whether you're advocating this as something that should be done. And if that's the case, then if you have, for example, instead of an isolated house or building, you have several, like coastal development area or city, for example, then I would guess that your heat exchange is going to become significantly less efficient due to the fact that your current there is very low. And so related to that, is it possible, is it plausible to try to find technological solutions to increase the flow of underground water and therefore heat exchange?
There are technologies to increase the flow of groundwater, but it's very expensive, and at the same time, sometimes you use some chemicals to, it's the fracking to increase the. So sometimes it's very dangerous. You have to know very, very well what are you doing, You have the problem of these things is when one project is bad, all the technology is bad. You know what happens with the nuclear? You know, it was very bad after the catastrophic episodes. But if you know what is going on, in theory, the risk is low. But of course, we have to count what is going on in the ground. Yeah. And yeah, this is an example with a single unique heat exchange, but it's not common here. You use sometimes you install more than one to obtain more energy from the ground and reduce the use of electricity, because there is not the panacea of energy, renewable energy, of course. There is to reduce your the money to heat and cold your buildings or your installations, and then you can support it with solar geothermal, solar energy or aeolic.
Yeah, regarding the model when you initialize this is sorry, there were a lot of things on the slide. It was
This one?
No, the one before. This is a 2D model, right?
Yes, 3D model indeed.
Yeah, because I was surprised how large the effect of one house is.
Yeah.
Also, it really depends on the 3 dimension, because I guess you will have like heat dispersion
Yes.
on this direction, right?
Yeah, there is a limitation of this model because the problem is 3D. And of course, there is some simple model there, but it takes a lot of time to run.
No, I get it. But this is like it must be like an overestimation of the effects, right?
Could be a lower estimation. Yeah. Because I try to use current temperatures of heat exchangers, because in Barcelona I work with other projects of installation, and they inject not inject 28 degrees, they inject 40 degrees, and in winter inject more or less 8 or something like that. But yeah, the effects will be more if we use as real temperatures of exchangers.
Yeah, but maybe you could consider like inserting some type of heat dissipation or some like heat reducer to simulate the dissipation across.
Okay. Yeah, no, I get it. Yeah, could be. Yeah, but this is a isotropic model. But in reality, the geology sometimes there is an isotropic. You have more velocities in horizontal rather than in vertical, because for the compactation of the geological layers. Yeah. There are different porosities in different layers, and
just to understand why I do understand the general issue here, but about the numbers is how comparable is this effect on the flux compared with variations in the aquifer? Because as far as I know here, for example, the variations, two things that characterize the high flow is that the transmissibility is rather high, so you have more flux than in other areas because of the geology, but also as far as I know from the geometric measurements, variations in sea level, in freshwater sea level, are really high. So those variations maybe override all these thermal effects.
yeah, of course, yeah.
So I don't know, for example, 1 meter in variation in your freshwater, how compares to the effect of the
It's one is if I don't remember, if I remember well, there is 2 meters more or less the oscillation of the seawater method is when we inject hot and cold. It's more or less like this. It's not so much if you compare with the oscillation of pumping groundwater. Of course, yeah. But this is a constant injection, a constant flood. But in reality, it's not constant. So I cannot consider. I didn't consider also the sea level. Okay, so there is different things that I want to apply in the future because they is very simple. I know I'm very aware of this, but
And the second question is about how, for example, we're in a climate warming scenario, and one of the things is that summer will become hotter. So how reliable is this technique, or can be used this as a general mechanism to just reduce colder buildings? So
yeah. Yeah, the problem.
can it be generalized? So,
Yeah. That's the thing. Is think about how works a fridge, where we store food, and there is a compressor. This is the same technology, more or less, simplifying it a lot, but it's more or less the same. We exchange temperature from the these pipes that. Some young people, I don't know if they know, but before the fridges behind are as pipes. Now there is aluminum and wood, something I don't know what to say. But you exchange energy with the atmosphere. You warm the air that are behind the fridge, while inside the fridge you are cold. So it is the problem is that we are injecting a lot of hot, and what is going on with this?
Well, one of the things is that I may anticipate is one of the things here is that most of the aquifers are nitrate rich, and because of the fertilization and so on. So that's really huge problem in Mallorca. So one of the things, and the aquifers actually they are important because they have the nitrifying bacteria. So if you change the temperature of the aquifer, probably that will influence the nitrification rate of the aquifer.
Yeah, it's very interesting thing because some months before we work in Barcelona looking for what is going on with the degradation of organic contaminants in the. So the temperature, increasing the temperature around the heat exchanger increase the degradation of these pollutants. Yes, but are only around, of course. But yeah, it's interesting. But what's going on with bacteria? No, could be growing a lot and clogging the aquifer. I don't know. It's very interesting field to study. Yeah, but some colleagues of Barcelona are studying this thing already. Yeah.
If one wants to cool only, would it be better to just have pipes that go down into the sea instead? I mean, it's much easier to build that than to drill a hole, which is a few kilometers deep, right?
Yeah.
Is there anything like that?
Yeah, there is some technology that works in.
All right. Yeah.
There is the pond lake, more or less like this.
So is it something that is used often, at least in coastal areas? Or
I don't know. I know some places with lakes to aquaculture to maintain the temperature of the lake, of the piscifactoria, how do you say, aquiculture. The place constant for increase the production of fishes. There is a big project in Japan. They extract groundwater, salty groundwater from the coast to use this thing, and then the hot water is released to the sea. It can move. Yes. Shallow release. Yeah. There is a different application of this. In Hawaii also they use this kind of technology in that manner. But the most common is in that is in this design, and sometimes it's using in the pipes en las cimentaciones. Las cimentaciones de los grandes buildings, we use these big columns to consolidate the structure of your building, including these pipes inside these columns. So you are reducing the cost a lot, because some of the main cost in these kind of projects is the drilling. Yeah, because you have to go more or less deep. Yeah, 125 is the standard in the state, but sometimes you require more in deep. And so, for instance, there is this kind of technologies is very common in places with invernaderos. Sorry, greenhouses. Yeah, I explained in this picture. Yeah, there is very common in greenhouses because they don't have money to perform deep drills. They take 2-3 meters of land, put these pipes, and then they put again this soil. Yeah, for it works with the solar energy that goes to the ground because it's very shallow.
No more questions? Okay, thank you, Rotman.
It's